So what you're going to want to do is you're going to create a class to go around the cursor's functionality to make it easier to use. So instead of having to say W move to position 3, 4 equal and set the value to be K, you're now going to be able to say my window at 3, 4 equals K, and it will go and make internally calls to cursors to make it so that happens and actually changes that character on the screen to become K. But it'll make it a lot easier for you to use instead of having to use the raw cursors functionality. Does that make sense? The reason why it's taking a little bit, it didn't take me that long to write the class, it's just taking long to get the testing done, because I have to make a fake cursors that has a fake cursors library that does the stuff that I'm then able to track to make sure that you're doing everything correctly. So that's taken me a little bit longer than I expected just to get some bare minimum stuff there. Anything else? Yeah. That's it's the code that you're writing there is very simple, because most of it you're like now I have window.move cursor. So inside you just say W move, right? Give it the window pointer to where you want to be at, all right? Or in your destructor you make sure to call delwin so that you delete the window. So most of the code that's there is really simple stuff, not too complicated. There is a little bit of inheritance there because I'm making you implement some interface of what functionality I want to be defined. But beyond that, it's not very complicated. But you will end up using this in your final project, if you so choose to, which you probably will because it makes life easy. And then we have to have a homework on exceptions too, which you'll probably take what you have there, and if somebody tries to go out of bounds, you'll throw some exceptions. Right? If you try to go to position 5, 9, but your screen's only a 3 by 3, you complain. Anything else? Yes. The next homework, again, will involve not really any polymorphism, but you will be implementing an interface. The final project will involve some polymorphism because you'll have to implement different AIs or different players there. And the way that you'll get their moves will be a little bit different depending on whether a human's playing or an AI's playing, and an AI's playing which AI. But don't get scared about AIs, because your AIs are going to be dumb, stupid things that just randomly pick places to play or implement a very basic strategy, not do anything super complicated. They're not going to be good. Anything else? Okay, then let's get back into what we were talking about, which was inheritance. So last time we talked about how you could override a parent's method. We talked about how you could call your parent's method. We talked about how you could call your parent's constructor to initialize yourself. And then we kind of left off on polymorphism. And we will go through quite a few examples of all of these topics. So if you have a parent pointer, you can point it at any of its children. So a parent pointer can point at a parent or any of the classes that are derived from it. If you only have a parent pointer pointing to a child, you can only access the parent portions of that child. Right? You can't access any of the child-specific parts because you only know about the parent portion of it. If the method that you call is a virtual method, the compiler is going to call the child method if the child has overridden it. And if it otherwise, if it's not virtual, it's going to call always the parent's method. This is really useful because you can get different behavior depending on, again, who you're pointing at. So again, I have a parent pointer P, a child pointer C, and then I have references to the things. You can also put a parent reference to any child object as well. That works. So I have my parent pointer P, right? Pointer equals the address of the parent. So pointer arrow greets and call hello. All right. Remember our child he's bilingual. He says buenos dias when he says hello. Right. And so if I put my parent pointer at the address of my child, it's going to call buenos dias instead, right? Because the child overloaded that method, and it's going to run the child's method then. Again, greet. If we just have these parent references, again, because they're parent references here, also have that same behavior as the pointers. So my parent reference dot greet is going to call hello. My child reference dot greet is going to call, say, buenos dias again. Because again, with the reference, you can call the child member as well, or call the child member if it's overridden it. Any questions here so far? So there are two types of casting. I guess there's technically three because you can do a side cast, but we're not going to talk about that one so much. So an upcast is when you convert a child pointer to a parent pointer. This is always acceptable. It's always okay to do because a child is always at least a parent. This is why we were able to do something like back here, right? Parent pointer P, right, pointer is equal to the address of C. What's the type of the address of C? What's the type of the address of C? Child pointer, right? The address of C is child pointer, right? The type of PTR is parent pointer. So I just took a child pointer, right? And I was able to cast it and put it into a parent pointer. Again, this was an implicit upcast. So you're correct. A parent is always at least, a child is always at least a parent because it has all the parent's parts that they inherit from them. But the child may have also added on more stuff. It could have added on more methods, more members, or it could have, as you also mentioned, overridden some of the parent's methods. So this means that any function that accepts a parent pointer or a parent reference as an argument, it's also perfectly fine for it to accept a child pointer or child reference. There's no problem here. Those are always convertible, right? But again, in those functions, you'd only be able to access the parent parts because you have a parent pointer. If a function has a return value of parent pointer or parent reference, that pointer or reference can point to or refer to a child object, right? So if my function is going to return a parent pointer, that parent pointer might actually be pointing to a child at that moment. It's fine, but again, you're only going to be able to access the child parts. The downcast is when you take a parent pointer and you attempt to transform it into a child pointer. You may need to be able to do this because you might need to be able to, you might need to access some of the child's members or the child's methods, right, that a parent doesn't have, right? So you need those child parts specifically. This is only okay to do if your parent pointer is really pointing at something of type child, right? If it's not and it's pointing at something of type parent, you're going to have issues here because the parent doesn't have those methods or doesn't have those members that you're trying to access. So again, if you want to be able to do that cast to a downcast, you have to either use static cast or dynamic cast to transform that pointer. The static cast you should only ever do from a parent pointer to a child pointer if you are absolutely 100% always know that this pointer is always going to point to something of type child. If you don't, right, and you make this cast, the cast will happen at compile time. Some code will try to run, and if it's not pointing at a child, it's going to break things at that point. It's going to break at runtime if you're not actually really pointing to a child. The other cast that you can use is dynamic cast. And dynamic cast you can use to attempt to cast a parent pointer or child pointer to a parent pointer. And if that thing you're really pointing to is of type child, you're going to get back a parent pointer. It'll actually be pointing to something. If it's not, you're going to get back a null pointer. And so you can check to see if this parent pointer really is pointing to something of type child before you try to dereference it. If you try to dynamic cast a reference, which you can also static cast a reference, again, only if you're 100% sure that it's really referring to that thing, it's going to raise an exception, which we'll be talking about next week or this week about what exceptions are. But it'll cause an error and your program's going to crash. You might ask, why would you bother to use dynamic cast? Or why would you bother to use static cast to try to transform your child pointers to parent pointers? If, dynamic casting is safer, right? You can check to see whether that cast was successful or not. The dynamic cast has runtime overhead. So if you do a dynamic cast, the compiler will insert code that actually has to be run that checks, okay, hey, is this thing really what we're pointing to? And so it'll slow things down, a marginal fraction of a second if that. But the static cast doesn't have any penalty or any overhead code that needs to be run. The pointer's type just changes at compile time. So we really want to think about what's happening. and no runtime overhead for that. Any questions here? So again, you should be able to see from what we talked about that you could check to see if something really is some type by using a dynamic cast, right? I attempt to dynamic cast to child 1. Oh, if it's not null, great, it must be child 1. Okay, otherwise I could try to cast it to child 2 type, right? Oh, that failed, right? Try to cast child 3 type. And the first one that's not null pointer, I can figure out what its type is. But in general, if you have some piece of code that has to keep checking all the types, it probably means you screwed up on your implementation. You might want to rethink how you have things built. Not always, but quite often that's the problem. Because the whole point of polymorphism is that we're not really supposed to have to know what the underlying type of that thing is supposed to be. It's just supposed to happen when we call the overloaded method. It does whatever it needs to do. But if we keep needing to know exactly what you are, there's probably issues there. Again, if you're doing a lot of type checking, you might want to ask yourself why you're doing it. Are you doing it because you want to call different methods based on the type of the object? Well, again, if that's the thing you're probably doing, you probably want to create an overloaded method in the parent and overwrite in the child and always to call that same method and let the inheritance take care of it, the virtual dispatch take care of it so that it goes to the child, in the case of the child when you're pointing to children, or goes to the parent when you're pointing to a parent. One other type that you might have is like you might have a vector of mixed types of things, and you might need to be able to go through and check who's who, who's what, right? Who's a child, who's a parent. That might be an okay case to do the static casting or the dynamic casting to be checking types, but again, it should be limited probably in most of your designs, how much time you're spending in your code checking what's the type of the thing that I have. Again, so here's an example where we wanted to access a child member from a parent pointer. Here's my child C, here's my parent P, here's my parent pointer, right? It's equal to the address of P. I have my child pointer, right? It's equal to a dynamic cast to a child pointer, a P pointer. Right now we're going to get back null pointer because currently P pointer is pointing to a parent. So the cast was unsuccessful. If I make my parent pointer point to the child and I attempt to do that dynamic cast, C pointer will have the address of this object and I'll be able to dereference it and access its members. It won't be null. And so now if I can do C pointer arrow cry, right, which was only a method defined on the child, right? The parent didn't know how to cry. So we can now call that child's method. Again, if we're doing the references, this also works. So we can dynamic cast to a child reference, right? Star P pointer. Star P pointer really is a child, so this cast will succeed. And again, I can do cry. But if I make my parent pointer equal to back to a parent, and I attempt to dynamic cast it to a child reference, this is going to cause an exception at runtime, and my code is going to die, more or less, because I'm not catching this exception. Any questions before we keep going? We're almost done, then we'll get to a lot of examples. So sometimes you're going to have a function in your parent class, but it doesn't make sense for the parent to provide anything here. As an example, you might have a class that represents some kind of connection. So you might want to be able to start a connection or end a connection or send data or receive data. But the way that this data should be sent or received or these connections started is going to depend entirely on the type of connection. Is it a Wi-Fi connection, an Ethernet connection, a point-to-point connection, right? All of these things are connections, but they're going to be very different in terms of how they operate. And the parent can't really provide any generic code for them to be able to use. But you might want to be able to create, again, in your program, different types of connections and not worry about what the underlying one is. So what you can do inside your class is you can declare a function as being virtual. By when you declare it, you set it equal to 0. If you do this, this means you're not providing an implementation, and it's going to make your class into an abstract class. And now your children are going to have to provide the implementation for that function. But They can do whatever they want. And they're going to have to provide that implementation if you want to be able to instantiate an instance of that class. Any class that has one or more pure virtual functions cannot be instantiated. You cannot create an instance of it. It'll be illegal, and the compiler will tell you can't do that because you have a method that has not been defined yet. It's pure virtual. Your children don't have to define that function, but again, they wouldn't be implementable. Somewhere down the line, somebody would have to implement it to make the instance of that class, to be able to create an instance of that class. Yeah, so like the point of just having like a pure virtual function is, if you've ever programmed in Java, it's like you can create something called like an interface, which it might describe like how, like what operations you're supposed to be able to do on these things or anything that is an instance of this. For example, you might define an interface for things that are supposed to be comparable, right? And anything that's supposed to be comparable has to implement an equals to and a not equals to operator, right? But in general, I don't know what you're supposed to do, but you just have to implement those things. Or you might want some things to be orderable, and if they're orderable, they have to implement a less than operator so that you know how to put them in order. Does that make sense? So an abstract class is a class that's, again, one or more pure virtual functions. You cannot create an instance of that class, but you can have a reference or a pointer to that class. That's perfectly fine. A class with no pure virtual methods is called a concrete class. It's something that you can instantiate. In this example that we have on the right, all the methods are virtual, but that's not a requirement for an abstract class. You might be able to define some of them. For the example that we just had, where you wanted things to be comparable, right? Equals, not equals to. You might say, well, somebody has to provide equals, right? But I'm going to provide the code for not equals, the generic, right? It's not. These two things are equal, right? That's what, doing that there. Or if you, again, you wanted things to be orderable, they have to define a less than. But if you have less than defined, you can actually define all of the other operations in terms of like less than, right? For example, like if you want to get equals, like equality, but all you have is less than, right? You could check to see if A is not less than B and B is not less than A, right? If A is not less than B and B is not less than A, they must be equal to each other. So you could provide some of that code if it made sense at a generic level to provide it. So over here, again, here's the class that we kind of mentioned as our example. We have our connection, which you can either start a connection, end a connection, send data through that connection, or receive some data. Yeah. So a pure virtual function is one of these that has an equals 0 at the end. It means I do not provide an implementation. A virtual function that's not pure virtual, you would have provided an implementation, which your child is now free to override. Anything else? So why might you bother with an abstract class, right? Seems like kind of pointless if you can't create an instance of it. The nice thing with an abstract class is, again, it's going to provide some uniform interface. Different children might implement the functionality in different ways, but because they're accomplishing the same task, it doesn't really matter how it's done. You could even swap out a different child, right, and not have to update any of your code besides where you call new, or where you basically set your pointer, with only one line of code if you found a better interface or better child that implemented that same interface. So how might you use this? Again, you make a pointer, maybe a smart pointer that of that type abstract class. You create space for one of the concrete child classes, and you put your parent pointer to it. So you might have something over here like I have a unique pointer to a connection equals con, right? Make unique Wi-Fi connection, right? Whatever parameters that Wi-Fi connection takes, which is perfectly fine because now I have a pointer to a Wi-Fi connection, right? And then I can go and I can, create, start the connection, end the connection, send the data, right? But you might decide, oh, well, maybe I don't want to be using Wi-Fi connections anymore. I want to use Ethernet connections instead. So instead, you could just say, con equals make unique Ethernet connection. And this code down here doesn't have to change at all, right? Because they're both connections. They're both opening connections, closing connections, and sending data. The way they do it's different, but I don't have to, on a lot of times, worry about how that's done. I could just sub them out as I felt like it. How is this different from templating? With templating, right, in general, like, if we go back over here, this is, like, you're right in that templating and inheritance are somewhat similar, but they're not quite the same. So over here, here's our class connection, right? How would you template it? Would you template it over the type of the internal connection that it held? Not really quite sure how you'd go about doing that, right? Templating is generally used for algorithms and containers, and it's where the logic of your code is the same, regardless of the type that you wanted it to implement on, right? With inheritance, right, and overriding, it's like, I always want something that's always going to be able to do these things, but I don't care, potentially how it's done, right? The different children can implement this class or implement this functionality however they choose to do so, right? But I want something that's able to implement that functionality. And then you can go and say, okay, you have to have at least these functions to be able to work. With the templating, you're not really able to like make any guarantees that this function supports this set of operators. If it doesn't, your code's probably going to compile, like fail to compile with some weird error that says like blah, 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 it doesn't exist. But with a compiler, with an inheritance, you would just say, hey, I guess like the error would be like, you didn't implement the function, more or less, when you're supposed to. So yeah, sometimes with the parents, you're able to provide a default implementation that makes sense, right? But not always. Another example for this that might be a little bit easier to understand is, let's think about, we had like shapes, right? Some things you can do on shapes are calculate the perimeter or calculate the area. But do you calculate the perimeter and area of all shapes the same way? No, but you might argue that a triangle is a shape. A circle is a shape. A rectangle is a shape, right? And so they might all have to provide like calculate area, right? Calculate perimeter functions. And now I can just have this shape pointer go through all of them, right? And say, hey, give me your area, give me your area, give me your area, give me your area, whatever I'm having to do, right? For example, you might be doing some like building program where the rooms are represented as shapes, right? And you need to figure out like what's the area of this house. You ask like what's the area of each of the rooms, and then add it all up. But with like a template, for one thing with like a template, like you could not have a vector of different types, right? Which you might need, right? You're like, oh, well, I need a vector that can have a circle and a square and a triangle, but you can't have that. But you could have a vector of shape, right? Or probably a vector of shape pointer, right? And these now, since we know that every shape has at least a get area function, we can call that get area function on it. Anything else? Again, you can't have this vector of mixed types, but if you wanted to try to emulate that effect, you could have a vector of parent pointers, right? And those parent pointers could point at instances of their children, and then when you call the overloaded methods, they go and they do the correct work. So again, we might have a vector of unique parent, right? A vector of unique parent pointers, and so we go through our vector, and if it's even, we're gonna put in a parent, and if it's odd, we're gonna put in a child, right? But these are pointers, so it's fine, right? But we can only ever access the parent functionality of the child because we only have parent pointers. It is possible to inherit from multiple parents. You get everything that they have. It's useful for when your class is more than one thing. When you do this, you separate who you inherit from with commas. If your parents both happen to have a member that has the same name, that's okay. You just have to specify whose you want to be using, but it does make things a little bit confusing. And so a lot of times when you're doing multiple inheritance, it's generally preferred to only inherit from multiple pure virtual classes, right? Inherit from multiple interfaces, so you provide all their functionality. It gets a lot messier when there's data. So, you might have a class, right, that has an instructor, right? And a class that's a researcher. Well, your professors, they're both instructors and researchers, right? So your professor class might inherit from both instructor and from researcher. And now when we want the professor to do their work, hey, we say, do the instructor's work and then do your researcher work, whatever that happens to be. Multiple inheritance tends to be not super common unless you're inheriting from multiple interfaces. But it does exist. Okay, so we had these last two slides and then we'll do 2 examples. One thing is the fact, oh yeah. Like, how do you declare a professor? Like, how does the professor call the instructors do work? It did it right here. That instructor : do work. So if you the instructor and researcher are not inside the professor's namespace. They're out. The instructor and researcher are outside of the professor's namespace. They're not inside of it. If these things were inside of other namespaces, like let's say that like instructor and was like inside like the teacher namespace, and researcher was inside like the science namespace for whatever reason, then if we wanted to do the instructors do work, we probably have to say like, teaching : instructor : do work. And to get the researcher, we have to do like science : researcher : do work to do the researcher's portion. So no, so like if you have an instance of a professor and you want to call that professor's do work method, and assuming your professor's name was Oak, it'd be oak.dowork. Well, we said that the professors do work did both the instructors and the researchers' work. Right? So you're saying outside the class, so outside the definition of the class, you want to be able to do only the instructor's portion of the work or only the researcher's portion. You'd probably have to provide other methods that were defined on the professor class called like do professor work, do researcher work, and then you could just do like oak.do professor or do researcher work, oak.do instructor work to make those things happen. Yeah.
If I have a
That's where things start to get a little ambiguous. It's still possible, and what would probably happen is you'd have to specify which one you wanted to do by casting it to that type. So you do a static cast to a pointer to make, and then do a's.work to make that one happen, or static cast to a b pointer to make it do the b's work. Is really rare, but yeah, it's still doable. If you found yourself in that situation, you probably have to do a little bit of Googling to figure out what the exact syntax was. Factory pattern again. This is useful for when you want to create different children classes based on different arguments. You can skip spaces. That was for the previous class. You can create a static class might be inside the base class that will return a pointer to the class base, return a pointer to the base class, but that pointer can point to any of the children classes. Again, you might do smart pointers, so you might have a unique pointer to a base called factory, and then you say which. So if which is equal to 1, return make unique child 1. Otherwise, if it's 2, return make unique child 2. Otherwise, return make unique child 3. Again, this pointer will be cast back into a base pointer, and so you'd only be able to access the base parts and not the individual parts of the child. This also assumes that all children could be constructed with the same arguments. If a child needed different arguments, then things might get a little bit more complicated and not so easy to do. One thing that you really want to make sure that you don't do is put a child inside of a parent. This is going to toss away all the child information parts. So you never want a function that returns something of type parent, and inside of that class you return a child. Syntactically it's legal, but all the child portions get thrown away because there's only space for the parent parts. Again, this is really easy to do when you either pass or return a value, pass or return a value, pass a parameter by value, or you return a value, so instead of returning a reference or accepting a reference. So over here, this might be something bad to do. So over here, we pass in our function takes in a b, and again, I guess we just attempt to static cast it to the derived member and then access that portion. And you can see out here, right, we'll have a base pointer BP. It equals a new derived object. I pass in, right, star BP. Everything seems like it should be fine, right? I put in a BP or a derived class, so it should be fine to access the derived members. But because this function took the value, the parameter by value, and this only takes in a base, we only keep the base parts of the child that we passed in, only the parent parts. And so all the child portions got thrown away. And so when attempting to do this, you're probably going to get a segfault because those parts don't exist anymore. It's just a super easy mistake to make, and the compiler's not so good about complaining to you about this. So again, this could be fixed by just, accepting a reference instead, because then you have a reference to the object, the child parts don't get thrown away, and you'd be able to access them. Or again, this can also happen when you want to return something of type parent, but then inside the function you return a child. All the child parts get lost. Okay, example time. Oh, here's all this stuff. Actually make a new one here. Oops. So again, let's make the example that we talked about earlier, right? We have a house, right? And the house is made up of some type of shapes for the rooms. And we want to be able to figure out, like, what's the area of this place. So over here, we might first start out with defining a new C++ class. And it might be called shape. And for this one, I'm going to create a header only. So what things might you want to figure out about the shape? Right? And so here might have double, like, calc or get area. This should be const. But with just a generic shape, do you know how to find the area of it? I don't know how to find the area of just some generic shape, right? I don't know if it's a triangle or a square or a rectangle or whatever, right? And so here I'm going to declare the function as being pure virtual, right? I'm not going to provide an implementation here. And then you might have like another function. We might want to be able to, like, get perimeter const. Everything makes sense so far? Yeah. Oh yeah. If we want to be able to override it, we do need that virtual keyword there. And then this didn't get added to my. So let's say we wanted to create a particular shape. So maybe we're going to create a new C++ class for a rectangle. And it didn't get added to the project. Oops, rectangle.h. So a rectangle, right, it is shape. Agreed? So here we're going to include shape.h, and to say that we are indeed a shape, well, we're going to inherit from shape. And because we've inherited from shape, we're going to have to provide a couple of methods. And if you want to, you can say over here, you go to code, and you can say override functions, and you can say, hey, which ones do you want to create overrides for? And you say, okay, and then boom, those functions are now here. And they're also now back here as well. But what other things might a rectangle have that differentiates it from another shape? It might have a length and a width. And so now for get area, oops, back. How can we get the area of a rectangle? Right, we just return like length times width. And for our perimeter, right, just 2 times length plus 2 times width. And now maybe we also have another class for a circle. I do want to add to my headers, thank you. Circle. And a circle and include shape. Well, a circle is also a shape, so again, public inheritance shape. And again, we can have it say code generate override functions, all of them. Great. But what does a circle have that's different from other things? It has a double radius, and that's, I think, like the only thing that we need to keep track of, right? So we might want to be able to get the area, get the perimeter, and maybe for circles, we might also want to be able to figure out some other things, right? We might want to also be able to get its radius and get its diameter. So we might define 2 other functions. Again, virtual if we want somebody to override them, which maybe we'll make them virtual for right now. So virtual double get radius const and virtual double get diameter const. And this is, get radius is pretty easy. Just return radius. Return 2 times get radius. And again, like some of the reason to, again, prefer using like the getters over using just the access of the raw members is that if somebody decided to override this class, right, and they wanted to change however radius was defined, right, now in getRadius, they could override the getRadius, and we would call the new overridden getRadius, and that would work correctly. We'd call our child's getRadius. Our area, right, that's like pi squared, so 3.14159, right? So return pi times pi. And our perimeter is going to be, const double. So here, our perimeter is going to be 2 times pi times our radius, if I remember my math correctly. Yeah. Yeah, probably like what would be better? Would it be better to make it a class member or better to make it something else? The static const double pi equals 3.14159. So now, back over here, we could get rid of this because we don't really need pi, a new pi for every single circle, just one pi for all the circles. And then back here in rectangle, again, we might have something like get length, get width. So code generates getters for length and width. And we'll also make them virtual just because. So now we're going to pop back out here to main, right? And let's say we, yes. Oh yeah, we probably do need constructors. That was the other thing I forgot about. Remember that you don't like inherit your parents' constructor, so everybody's going to have their own constructor. So code generate constructor. I need both the length and the width. And then for my circle, const expression. Okay. Code generate constructor. You have to give me the radius. So we'll pop back over here to main, and we are going to include shape.h, circle.h, rectangle.h, and we also were going to want to include vector. Yeah, it is. I fixed it so that it would automatically add it in. I also want to include memory. So we're out of time now, but what we'll do on Wednesday is we'll create a vector of shapes, and we will find the area of all of these shapes and find the perimeter of all of these shapes. And our code will look nice and easy. Just call get area or get shape on, or get area or get perimeter on that shape, and it will either go to the circle or go to the rectangle, depending on whether that guy happens to be a circle or rectangle.